I thought I'd start with telling you or showing you the people who started JPL. Well, they were a bunch of kids. They were kind of very imaginative, very adventurous, so they were trying at Caltech to mix chemicals and see which one blows up more. Well, I don't recommend that you try to do that now. In actuality, they blew up a shack, and Caltech told them, hey, you go to the Arroyo and really do all your tests in there. So that's what we call our first 5 employees during the tea break, in here. As I said, they were adventurous people. Matter of fact, one of them was kind of part of a cult which was not too far from here on Orange Grove, and unfortunately blew up himself because he kept mixing chemicals and trying to figure out which one were the best chemicals. So that gives you kind of flavor of the kind of people we have there. We try to avoid blowing ourselves now. This one I thought I'll show you. Guess which one is a JPL employee, out of this crowd. I tried to come like him this morning, but as I walked out, then it was too cold, and I said I'd better put my shirt back on. But more importantly, the reason I wanted to show this picture, look where the other people are looking and look where he is looking. Wherever anybody else look somewhere else and go do something different, on doing that. And that's kind of what has been the spirit of what we are doing. And I want to tell you a quote from Ralph Emerson that one of my colleagues, put on my wall in my office, and it says, "Do not go where the path may lead. Go instead where there is no path and leave a trail." And that's my recommendation to all of you. Look where everybody is doing what they are doing, go do something completely different. Don't try to improve a little bit on what somebody else is doing, because that doesn't get you very far. And in our early days, we used to work a lot on rockets, but we also used to have a lot of parties. As you can see that one of our parties, a few years ago. But then a big difference happened about 50 years ago after Sputnik was launched. We launched the first American satellite, and that's the one you see on the left in there. And here we made a 180 degrees change. We changed from a rocket house to be an exploration house. And that was done over a period of a couple of years, and now we are the leading organization, exploring space on all of your behalf. But even when we did that, we had to remind ourselves that sometimes there are setbacks. So you see on the bottom, that rocket was supposed to go upward. Somehow it ended going sideways. So that's what we call the misguided missile. But then also, just to celebrate that, we started an event at JPL for misguided missile. So we used to have a celebration every year and select. There used to be competition and parades and so on. It's not very appropriate to do it now. Some people tell me to do it, and then, well, that's not really proper, these days. So we do something a little bit more serious, and that's where you see in the last Rose Bowl, when we entered one of the floats, that's more on the play side, and on the right side, that's the rover just before we finished its testing to take it to the Cape to launch it. These are the rovers that you have on Mars now. So that kind of tell you about kind of the fun things, and the serious things that we try to do. But I thought I'm going to show you a short clip of one of our employees to kind of give you an idea about some of the talent that we have at JPL.
Aware of Safety is an instrumental rock band. It branches on more of the experimental side. There's the improvisational side of jazz. There's the heavy-hitting sound of rock. Being able to treat sound as an instrument and be able to dig for more abstract sounds and things to play live, mixing electronics and acoustics. The music's half of me, but the other half, I've landed probably the best gig of all. I work for the Jet Propulsion Lab, and I'm building the next Mars rover. Some of the most brilliant engineers I know are the ones who have that sort of artistic quality about them. You got to do what you want to do. And anyone who tells you you can't, listen to them. Maybe they're right. I doubt it. Tell them where to put it, and just do what you want to do. I'm Morgan Hendry. I'm NASA.
Now, moving from the play stuff to the serious stuff, always people ask, why do we explore? Why are we doing all of these missions, and why we are exploring them? Well, the way I think about it is fairly simple. Somehow, 13 billion years ago, there was a Big Bang, and you heard a little bit about the origin of the universe. But somehow, what strikes everybody's imagination, lots of people imagine, somehow from that original Big Bang, we have this beautiful world that we live in today. You look outside, you have all that beauty that you see, all that life that you see around you, and here we have intelligent people like you and I who are having a conversation here. All that started from that Big Bang. So the question is, how did that happen? How did that evolve? How did the universe form? How did the galaxies form? How did the planets form? Why is there a planet on which there is life which have evolved? Is that very common? Are there life on every planet that you can see around the stars? So we literally are all made out of stardust. We started from those stars, we are made of stardust. So next time you are really depressed, look in the mirror and you can look and say, I'm looking at the star here. You can skip the dust part. But literally we are all made of stardust. So what we are trying to do in our exploration is effectively write the book of how things have came about as they are today. And one of the first or the easiest place that we can go and explore that is to go toward Mars. And the reason Mars takes particular attention, it's not very far from us. It takes us only 6 months to get there, 6 to 9 months at the right time of the year. It's a planet somewhat similar to Earth. It's a little bit smaller, but the land mass on Mars is about the same as the land mass on Earth. They don't take the oceans into account. It has polar caps. It has an atmosphere, somewhat thinner than ours. So it has a weather. So it's very similar to some extent. And you can see some of the features, on it, like the Grand Canyon on Mars, or what we call the Grand Canyon on Mars, is like the Grand Canyon on Earth, except a hell lot larger. So it's about the size, of the United States. It has volcanoes on it. And that's Mount Olympus on Mars, which kind of huge volcanic shield on that planet. And if you look at the height of it and you compare it to Mount Everest, you see it will give you an idea of how large that Mount Olympus, is relative to Mount Everest. So it basically dwarfs, Mount Everest here on Earth. So that gives you an idea of the tectonic events or volcanic events which have happened on that planet. Recently, from one of our satellites, to show you that it's Earth-like, we caught a landslide occurring as it was happening. So it is a dynamic planet, and activity is going on it as we speak today. And these rovers, people wonder now, what are they doing today? So I thought I will show you a little bit what they are doing. This is one very large crater. Geologists love craters, because craters like you dig a big hole in the ground without really working at it, and you can see what's below the surface. So this is called Victoria Crater, which is about a few football fields in size. And if you look at the top left, you see a little teeny dark dot. This picture was taken from an orbiting satellite. If I zoom on it, you can see that's a rover on the surface. So that was taken from orbit. We had the camera zoom on the surface, and we actually saw the rover on the surface. And we actually used the combination of the satellite images and the rover to actually conduct science, because you can observe large areas and then you can get those rovers to move around and basically go to certain location. So specifically what we are doing now is that rover is going down in that crater. As I told you, geologists love craters. And the reason is, many of you went to the Grand Canyon, and you see in this wall of the Grand Canyon, you see these layers. And what these layers, that's what was the surface used to be a million years ago, 10 million years ago, 100 million years ago, and you get deposits on top of them. So if you can read the layers, that's like reading your book, and you can learn the history of what happened in the past in that location. So what you are seeing here are the layers on the wall of that crater, and the rover is going down now, measuring, the properties and analyzing the rocks as it's going down, that canyon. Now, it's kind of a little bit of a challenge driving down a slope like this. If you were there, you wouldn't do it yourself. But we really made sure we tested those rovers before we got them down, and or that rover, and made sure that it's all working well. Now, when I came last time, shortly after the landing, I think it was like 100 days after the landing, I told you, well, we're surprised that those rovers are lasting even 100 days. Well, here we are 4 years later, and they are still working. Now you say, Charles, you were really lying to us and so on. But that's not true. We really believe they were going to last 90 days or 100 days because they are solar powered. And Mars is a dusty planet. So we expected that dust will start accumulating on the surface. And after a while, we don't have enough power, to keep them warm. Well, I always say it's important that you are smart, but every once in a while, it's good to be lucky. And that's what we found out. It turned out every once in a while, there are dust devils which come by on Mars, as you are seeing here. And when the dust devil comes over the rover, it just cleans it up. And it's like a brand new car that you have. And that's literally why they have lasted so long. I mean, now we designed them reasonably well, but that's exactly why they are lasting that long and still all the science data. Now, the two rover, each one of them is kind of getting old. One of the wheels is stuck, is not working, one of the front wheels. So what we're doing, we're driving it backward. And the other one has arthritis, so the shoulder joint, is not working very well, so it's walking like this, and we can move the arm, that way. But still, they are producing a lot of scientific data. Now, during that whole period, a number of people got excited, outside the science community about these rovers. So I thought I'll show you a video just to give you a reflection about how these rovers are being viewed by people other than the science community. So let me go on the next short video.
Okay,
by the way, this video is pretty accurate of how the landing took place, about 4 years ago.
Okay, we have parachute online. Okay, inflate airbags. Open. Camera off. I'm gonna have a picture right now.
That's about what happened in the mission operation room, not exactly like this.
Now, if there is life, the Dutch will find it. Wait. What is he doing? What is that?
Not a bad ad for that. So anyway, let me continue on showing you a little bit about the beauty of that planet. As I said earlier, it looked very much like Earth. So you see sand dunes. It looks like I could have told you these are pictures taken from the Sahara Desert to someone, and you'd have believed me, but these are pictures taken from Mars. But one area which are particularly intriguing for us are the northern region of Mars, close to the North Pole, because we see ice caps, and we see the ice cap shrinking and expanding. So it's very much like you have in northern Canada. And we wanted to find out, and we see all kinds of glacial features on it. So we wanted to find out, actually, what is that ice made of? And could that have embedded in it some organic material? So we have a spacecraft which is heading toward Mars called Phoenix. And that spacecraft will land 17 days, 7 hours, and 20 seconds from now, so you can adjust your watch. So it's on May 25th, around almost just before 5 o'clock our time here on the West Coast. Actually, we will be landing on another planet. And as you can see, this is a picture of the spacecraft put on Mars. But I thought, just in case you are going to miss that show, in 17 days, I'll show you kind of a little bit what's going to happen. And that's what we call the 7 minute of terror. The soil and take samples that we put them in an oven and actually heat them and look what gases will come from it. So this was launched about 9 months ago. We'll be coming in at 12,000 miles per hour, and in 7 minutes we have to stop and touch the surface very softly so we don't break that land.
Phoenix is the first Mars-bound mission. It's the first mission that's going to try to land near the North Pole of Mars. And it's the first mission that's actually going to go try and reach out and touch water on the surface of another planet.
Where there tends to be water, at least on Earth, there tends to be life. And so it's potentially a place where life could have existed on the planet in the past.
The main purpose of EDL is to take a spacecraft that is traveling at 12,500 miles an hour and bring it to a screeching halt in a soft way in a very short amount of time.
We enter the Martian atmosphere. We're 70 miles above the surface of Mars, and our lander is safely tucked inside what we call an aeroshell.
Looks kind of like an ice cream cone, more or less.
And on the front of it is this heat shield, this saucer-looking thing that has about a ½ inch of essentially what's cork on the front of it, which is our heat shield. Now, this is really special cork, and this cork is what's going to protect us from the violent atmospheric entry that we're about to experience.
Friction really starts to build up on the spacecraft, and we use the friction when it is flying through the atmosphere to our advantage to slow us down.
From this point, we're going to decelerate from 12,500 miles an hour down to 900 miles an hour.
The outside can get almost as hot as the surface of the sun.
The temperature of the heat shield will reach 2,600 degrees Fahrenheit. The
But the inside doesn't get very hot. It probably gets about room temperature.
There is this window of opportunity within which we can deploy the parachute.
If you fire the chute too early, the parachute itself could fail. The fabric and the stitching could just pull apart. And that would be bad.
In the first 15 seconds after we deploy the parachute, we'll decelerate from 900 miles an hour to a relatively slow 250 miles an hour. We no longer need the heat shield to protect us from the force of atmospheric entry, so we jettison the heat shield, exposing for the first time our lander to the atmosphere of Mars.
After the heat shield has been jettisoned and the legs are deployed, the next step is to have the radar system begin to detect how far Phoenix really is from the ground.
We've lost 99% of our entry velocity, so we're 99% of the way to where we want to be. But that last 1%, as it always seems to be, is the tricky part.
Now, the spacecraft actually has to decide when it's going to get rid of its parachute.
We separate from the lander going 125 miles an hour at roughly a kilometer above the surface of Mars, 3,200 feet. That's like taking 2 Empire State Buildings and stacking them on top of one another.
That's when we separate from the back shell, and we're now in free fall. It's a very scary moment. A lot has to happen in a very short amount of time.
So it's in a free fall, but it's also trying to use all of its actuators to make sure that it's in the right position to land.
And then it has to light up its engines, right itself, and then slowly slow itself down and touch down on the ground safely.
Earth and Mars are so far apart that it takes over 10 minutes for a signal from Mars to get to Earth. And EDL itself is all over in a matter of 7 minutes. So by the time we even hear from the lander that EDL has started, it'll already be over.
We have to build large amounts of autonomy into the spacecraft so that it can land itself safely.
EDL is this immense technically challenging problem. It's about getting a spacecraft that's hurtling through deep space and using all this bag of tricks to somehow figure out how to get it down to the surface of Mars at 0 miles an hour. It's this immensely exciting and challenging problem.
Hopefully it all will happen the way you saw it in here. So it will be a very tense moment, you know, as we are watching that spacecraft landing on another planet. So now let me talk about the next things that we are doing. So we are in the process, as we speak, of actually designing the next rover that we are going to be sending to Mars. So I thought I will go a little bit and tell you kind of the steps, you know, we go through. It's very similar to what you do when you design your product. As you saw a little bit earlier when we were doing the Phoenix one, we have to take into account the heat that we are going to be facing. So we have to study all kinds of different materials, the shape that we want to do. In general, we don't try to please the customer here. What we want to do is to make sure we have an effective, you know, an efficient, you know, kind of a machine. First, we start by when we want to have our employees to be as imaginative as they can. And we really love being close to the art center because we have, matter of fact, one of the alumni from the art center, Eric Nyquist, have put a series of displays, far-out displays, you know, in our what we call mission design or spacecraft design room, just to get people to think wildly about things. We have a bunch of Legos, so as I said, this is a playground for adults, so they sit down and try to play with different shapes and different designs. Then we get a little bit more serious, so we have what we call our CAD cams and all the engineers who are involved or scientists who are involved who know about thermal properties, know about design, know about atmospheric interaction, parachutes, all of this thing, which they work in a team effort and actually design a spacecraft in a computer to some extent, so to see does that meet the requirement that we need. On the right, also, we have to take into account the environment of the planet where we are going. If you are going to Jupiter, you have a very high radiation, you know, environment. It's about the same radiation environment close by of Jupiter as inside a nuclear reactor. So just imagine you take your PC and throw it into a nuclear reactor and it still has to work. So these are kind of some of the little challenges, you know, that we have, we have to face. If we are doing entry, we have to do tests of parachutes. You saw in the video parachute breaking, that will be a bad day, you know, if that happens. So we have to test, because we are deploying these parachutes at supersonic speeds. We are coming at extremely high speed and we are deploying them to slow us down. So we have to do all kinds of tests to give you an idea about the size, you know, of that parachute relative to the people standing there. Next step, we go and actually build some kind of test models and actually test them, you know, on, in the lab at JPL or in what we call our Mars yard. We kick them, we hit them, we drop them, just to make sure we understand where would they break. And then we back off from that point. And then we actually do the actual building and the flights. And this next rover that we're flying is about the size of a car. That big shield that you see outside, that's a heat shield which is going to protect it. And that will be basically built over the next year, and it will be launched June a year from now. Now, in that case, because it was a very big rover, we couldn't use airbags. I know many of you kind of, last time after I talked, you said, wow, that was a cool things to have those airbags. Unfortunately, this rover is like 10 times the size of the, mass-wise of the other rover, or 3 times the mass. So we can't use airbags. So we had to come up with another ingenious idea of how do we land it. And we didn't want to take it propulsively all the way to the surface because we didn't want to contaminate the surface. We wanted the rover to immediately land on its legs. So we came up with this ingenious idea, which is used here on Earth from helicopters. Actually, the lander will come down to about 100 feet and hover above that surface for 100 feet, and then we have a sky crane, which will take that rover and land it down on the surface. Hopefully it all will work, it will work that way. And that rover will be more kind of like a chemist. What we are going to be doing with that rover as it drives around, it's going to go and analyze the chemical composition of rocks. So it will have an arm which will take samples, put them in an oven, analyze them, crush them, analyze them. But also if there is something that we cannot reach because it's too high on a cliff, we have a little laser system which will actually zap the rock, evaporate some of it, and actually analyze what's coming from that rock. So it's a little bit like Star Wars, but it's real. It's real stuff. And also to help the community so you can do ads on that rover, we are going to train that rover to actually, in addition to do this, to actually serve cocktails, also on Mars. So that's kind of give you an idea the kind of, fun things we are doing on Mars. I thought I'd go to the Lord of the Rings now and show you some of the things we have there. Now, the Lord of the Rings has 2 things play to it. One, it's very attractive. Planet. It just has the beauty of the rings and so on. But for scientists, also the rings have a special meaning because we believe they represent on a small scale how the solar system actually formed. The belief, some of the scientists believe that the way the solar system formed, that the sun, when it collapsed and actually created the sun, a lot of the dust around it created rings, and then the particles in those rings accumulated together and they formed bigger rocks, and then that's how the planets were formed. So the idea is by watching Saturn, we're actually watching our solar system in real time being formed on a smaller scale. So it's like a test bed for it. So let me show you a little bit on what that Saturnian system looks like. First, I'm going to kind of fly you over the rings. By the way, all of this is real stuff. This is not animation or anything like this. This is actually taken from the satellite that we have in orbit around Saturn, that the Cassini. So, and you see the amount of detail that are in those rings, which are the particles. Some of them are agglomerating together to form larger particles. So that's where you have these gaps, is because a small satellite, is being formed in that location. Now, you think that those rings are very large objects. Yeah, they are very large in one dimension. In the other dimension, they are paper thin. Very, very thin. What you're seeing here is the shadow of the ring on Saturn itself. And that's one of the satellites which was actually formed on that one. So think about it as a paper-thin, huge area of many hundreds of thousands of miles, which is rotating. And you have a wide variety of kind of satellites which were formed, each one looking very different and very odd, and that keeps scientists busy for tens of years trying to explain this and telling NASA we need more money so we can explain what these things look like, or why they formed that way. Well, there were 2 satellites which were particularly interesting. One of them is called Enceladus. It's a satellite which was all made of ice, and we measured from orbit it made of ice, but there was something bizarre about it. If you look at these stripes in here, what we call tiger stripes, when we flew over them, all of a sudden we saw an increase in the temperature, which said that those stripes are warmer than the rest of the planet. So as we flew away from it, we looked back, and guess what? We saw geysers coming out. So this is the Yellowstone, of Saturn. We're seeing geysers of ice, which is coming out of that planet, which indicate that most likely there is an ocean, below the surface, and somehow through some dynamic effect, we're having these geysers which are being, emitted from it. And the reason I showed a little arrow there, I think that should say 30 miles. We decided a few months ago to actually fly the spacecraft through the plume of that geyser. So we can actually measure, what that geyser made of, or the material what is made of. That was sporty also, because we were worried about the risk of it, but it worked pretty well. We flew at the top of it. And we found that there is a fair amount of organic material which is being emitted in combination with the ice. And over the next few years, as we are keep orbiting Saturn, we're planning to get closer and closer down to the surface and make more accurate measurements. Now, another satellite also attracted a lot of the attention, and that's Titan. And the reason Titan is particularly interesting, it's a satellite bigger than our moon, and it has an atmosphere. And that atmosphere is as dense as our own atmosphere. So if you were on Titan, you will feel the same pressures that you will feel in here. Except it's a lot colder, and that atmosphere is heavily made of methane. Now, methane gets people all excited because it's organic material. So immediately people start thinking, could have life evolved in that, in that location when you have a lot of organic material. So people believe now that Titan is most likely what we call a prebiotic planet, because it's so cold. Organic material did not get to the stage of become biological material, and therefore life could have evolved on it. So it could be Earth frozen of 3 billion years ago before life actually started on it. So that's getting a lot of interest. And to show you some example of what we did in there, we actually dropped a probe which was developed by our colleagues in Europe. We dropped a probe as we were orbiting Saturn. We dropped a probe in the atmosphere on Titan, and this is a picture of an area as we were coming down. Just looked like the coast of California for me. You see the rivers which are coming along the coast, and you see that white area which looks like Catalina Island, and that looks like an ocean. And then with an instrument we have on board, a radar instrument, we found there are lakes, like the Great Lakes in here. So it looks very much like Earth. It looks like there are rivers on it, there are oceans, there are lakes, we know there are clouds, we think it's raining also on it, so it's very much like the cycle on Earth, except because it's so cold, it could not be water, because water would have frozen. What it turned out that all what we are seeing, all these liquids, are made hydrocarbon and ethane and methane, similar to what you put in your car. So here we have a cycle of a planet which is like our Earth, but it's all made of ethane and methane and organic material. So if you were on Mars, on Titan, you don't have to worry about $4 gasoline. You just drive to the nearest lake, stick your hose in it, and you got your car filled up. On the other hand, if you light a match, the whole planet will blow up. So in closing, I thought I want to close by a couple of pictures, and just to kind of put us in perspective. This is a picture of Saturn taken with a spacecraft from behind Saturn, looking towards the sun. The sun is behind Saturn, so we see what we call forward scattering. So it highlights all the rings. And I'm going to zoom. I'm not sure you can see it very well, but on the top left, like around 10 o'clock, there is a little teeny dot, and that's Earth. You barely can see ourselves. So what I did, I thought I'll zoom on it. So as you zoom in, you can see Earth, just in the middle here. So we zoomed all the way on the Art Center. So thank you very much.